NVIDIA just dropped something that could completely change how we teach robots to move. And honestly, almost nobody saw this coming. We're talking about DreamDojo, an open source robot brain that learned from 44,711 hours of regular humans going about their daily lives. And it can now run a full robot simulation in real time, improve a robot's success rate by 17% before it even touches a real object, and match real-world results with a 0.995 Pearson correlation score, which is basically perfect. And the crazy part is that NVIDIA did not use a single traditional physics engine. The system just dreams up what happens next directly in pixels. So let us talk about it. Alright, first let us talk about the biggest problem in robotics right now. Because without understanding this, DreamDojo does not make sense. If you want to build a robot that can fold laundry, pour a glass of water, or sort food, you need to train it first, right? And to train it, you need a simulator. A fake world where the robot can practice thousands of times without breaking anything. The old way to build these simulators was to manually code every single physics rule. You had to program how gravity works, how water cools, how objects bounce, how a soft cloth folds differently than a hard box. This is extremely slow, costs a huge amount of money, and still never quite matches the messiness of the real world. That is the wall robotics has been hitting for years. Here's the thing. NVIDIA looked at that problem and basically said, what if we skip all of that manual physics coding? What if instead we just show the system tens of thousands of hours of real humans doing real things and let it figure out the physics on its own? That is exactly what DreamDojo is. It does not simulate the world with code, it predicts the next frame of video, one after another, like dreaming what should happen next. And it learned to dream by watching 44,711 hours of humans going through real everyday tasks. The dataset they built for this, called DreamDojo HV, is the largest collection of first-person human video ever used for this kind of robot training. We are not just talking about a lot of hours. The data covers 6,015 unique tasks, over 1 million separate action recordings, 9,869 different scenes, and 43,237 unique objects. That is an insane variety of situations. And the key idea is that humans already understand physics in a very deep way. When you pour water, you tilt the bottle just right without thinking. When you fold a shirt, your hands know the weight and texture automatically. DreamDojo absorbed all of that common sense knowledge just by watching. They then built two versions of the model, a 2 billion parameter version and a much larger 14 billion parameter version, and training them used 100,000 NVIDIA H100 GPU hours, which gives you a sense of the scale of this project. Now, here is where it gets interesting, because there is a real technical problem hiding underneath all of this. Human video does not come with robot instructions. When you watch a person pick up a cup, the video does not tell you the exact joint angles of their arm or the force applied by their fingers. That data simply does not exist in the video, and robots need precise action signals to learn from. So NVIDIA had to solve something tricky. How do you turn raw human video into something a robot can actually understand and copy? The answer is what they call continuous latent actions. The team built a specific encoder, a spatiotemporal transformer VAE, which is basically a system that looks at two video frames back to back and pulls out a 32-number summary of exactly what moved and how. This 32-number package captures the most important motion between those two frames. It strips away background noise and focuses only on the action itself. So instead of trying to map human arm movement directly to robot arm angles, which would never quite line up, the system creates this middle layer, a motion fingerprint that works across different bodies. The robot does not need to move exactly like a human, it just needs to understand the same physics. And this approach means DreamDojo can transfer what it learned from watching people to completely different robot designs without needing to be retrained from scratch each time. And in fairness, this is not the first time someone has tried to learn from human video for robotics. Other labs have explored similar ideas, but the scale here is different. Most prior work used much smaller datasets with maybe a few hundred hours of data. 44,711 hours is on a completely different level, and that scale is what makes the physics understanding so much richer and more generalizable. The model itself is built on top of Cosmos Predict 2.5, which is NVIDIA's own video generation system, and uses something called the 1.2.2 tokenizer. But NVIDIA's team did not just plug it in and call it done. They made three specific improvements to actually make it work well. The first one is the relative accents. Instead of giving the model absolute robot positions like arm is at coordinate x, they give it relative changes, like arm move 5 degrees to the left. This sounds like a small detail, but it makes a massive difference because the model generalizes across thousands of different starting positions instead of memorizing specific locations. The second upgrade is chunked action injection, where 4 consecutive actions are fed into each video frame. This keeps the model's understanding of time lined up correctly with how the video is actually compressed. The third piece is a new training signal called temporal consistency loss, which basically punishes the model every time an object in the video moves in a way that breaks real physics. It constantly keeps the simulation grounded in how objects actually behave in the real world. Now, here is the part that surprised a lot of researchers. Running a diffusion-based video model in real time is basically impossible in its standard form. These models normally need dozens of processing steps to generate each frame, which makes them way too slow for anything interactive. NVIDIA solved this using a process called self-forcing dysplasia. They trained a faster student model to copy the outputs of the slower full model. And through that process, they reduced the number of processing steps from 35 down to just 4. The result is a system that runs at 10.81 frames per second, fast enough to simulate a robot moving in real time. And it stays stable for a full 60 seconds of continuous playback, which is 600 frames in a row without losing track of what is happening. The distillation training alone ran on 64 NVIDIA H100 GPUs. So this is not something any small team could easily reproduce, even though the final model is now open source. And the performance numbers are where things get really serious. The 2 billion parameter version scores 62.5% on physics correctness and 63.45% on action fallen. The 14 billion parameter version jumps to 73.5% physics correctness and 72.55% action falling. These are measured by blind evaluators checking whether the simulated physics actually makes sense and whether the robot in this simulation follows commands correctly. Now, those numbers are not perfect yet. And that is important to be honest about. There is still roughly a 27% gap before the system can be fully trusted for all robot tasks. It still makes physics mistakes. It can be wrong about how objects fall or how they interact in unusual situations. But here is where the real world results become impressive. When researchers tested DreamDojo as a tool to help a real robot pick and pack fruit, the robot's success rate improved by 17%. Simply because it was able to use DreamDojo to simulate and think through multiple possible moves before choosing one. Compared to just picking randomly, that planning approach doubled the success rate. And when they measured how closely the simulator matched real outcomes across multiple tasks, they got a Pearson correlation of 0.995 with a mean maximum rank violation of only 0.003. To put that simply, if DreamDojo says option A will work better than option B, it is almost always right when you test it in the real world. That kind of reliability is what actually makes a simulator useful in practice. One application that caught a lot of attention in the community is live teleoperation. Researchers used a Pico VR controller connected to a regular desktop running on NVIDIA RTX 5090 to control a virtual robot inside DreamDojo in real time. The idea is that instead of buying a real robot and risking damage every time you try to collect training data, you can now do the whole thing inside the simulator at a fraction of the cost. This also opens the door for people all around the world to generate robot training data without needing access to expensive physical hardware. The bigger picture here is that robots have always struggled with the gap between fake training environments and the real world. Classic simulators look clean and perfect but fail the moment they meet a real kitchen or a cluttered warehouse floor. DreamDojo is one of the most serious attempts to close that gap, not just by making fake worlds more perfect, but by teaching the AI what the real world actually looks like using real human experience. And the fact that 17% real world improvement can come from a system that never touched the physical robot once is a sign of where this whole field is going. That is where we will wrap it up. The question I keep coming back to is whether a human video data alone can eventually close that final 27% gap in physics understanding, or whether robots will always need some amount of real world experience to get all the way there. Drop your thoughts below. Make sure you are subscribed, hit the like button, and I will see you in the next one.